Hello everyone, greetings of the day. My name is Orko De, your physics teacher, and we are going to start our today's discussion with a very small assignment I'm going to give you. That is, you have to find out through where your house wiring is done. That means you clearly know that nowadays we use concealed wiring, so wires are not visible. Okay, you can only see your switchboard and switches. So how can we find out where the wiring is done? Any idea, anyone? Let me give you a hint. We can use a magnetic compass. Yes, so absolutely correct. Good thinking, everyone. So we are going to use the magnetic effect of electric current. Anybody remembers what is it about? Yes. So whenever there is a current flowing through the conducting wire, there is a magnetic field produced, right? And that is called magnetic effect of electric current. And this is first observed by Oersted from Oersted's experiment. Do you remember about the Oersted experiment? Yeah. So initially there was a wire. There is no current passing through it. Now there is a compass placed, magnetic needle also you can call it, placed below there. And then the current was allowed to pass through the conducting wire. Now in which direction the deflection is going to happen? Anybody remember? Yes, the needle is going to deflect in that direction. So the compass is going to look slightly differently. Now the compass is going to look like that. So the north is going to be in this direction. Now, if you're going to change the direction of the current, the direction of the deflection is also going to change. That means the compass is going to deflect in this direction now. Okay. So this is going to be the situation after deflection. The north is going to be in that direction. So it is very clear. From Oersted experiment, we can find that out. Now, what about the direction of the magnetic field? Okay, so deflection definitely points out the direction of the magnetic field, but we can also use the right thumb rule to find out the direction of the magnetic field. So let's say this is the current. So the current is, we are going to use our thumb to point out in the direction of the current, and the fingers are going to curling around. The thumb is going to point out the direction of the magnetic field. Okay, so the fingers are going to look like that, and they are going to point out the direction of the magnetic field. So B basically magnetic field, and they are going to be pointed out by the fingers. Okay, this is it. Now the magnetic fields are going to look like concentric circles about this conducting wire, and the direction we have already found out like that. Okay, clear? Now, if I'm going to ask you, now you already found out the direction of the magnetic field. What should be the magnitude of the magnetic field? Yes, so that is what we are going to talk about today. In today's class, you are going to learn. So magnitude of the magnetic field due to a current passing through a conducting wire. Okay, and let us take a straight conducting wire, or any, we can also take it a curved conducting wire, doesn't matter. So let us take a curved one. Okay, so this is the conducting wire, and let's say this is the battery connected to the conducting wire, and current flowing in this direction. Okay, now we need to find out the magnetic field at this particular point P. We call it observation point, where the magnetic field to be observed. Now, there are different ways we can actually do it. We know already that current flows due to the flow of electrons. So for each electron, we can find out the magnetic field at P and then add them up. And definitely, as it sounds, this is going to be very, very difficult. So we are not going to do that. Okay. So what we're going to do, we are going to divide the whole conducting wire into the small fragments. We call it current element. So let's say there are let us divide this conducting wire into different current elements. Let's say one of them is like that. This is called current element. So let me point it out for you. It is called current element. So what we are going to do, we are going to find the magnetic field at point P for different current elements, and we are going to sum them up or integrate for all of them. Okay, so that is what we are going to do over here as well. And let us say dl is the current element, and dl is a vector quantity, as you can see, and its direction is along the direction of the flow of current. So this is the direction of the flow of current, and DL is also in that direction. Now let us take an origin. Let's say the midpoint is O, and we are going to find out the position vector of point P with respect to that O, and we call it R. Okay, and the angle between this DL current element and R, let's say it is theta. Okay, so it is theta. Okay, now Biot and Savart have done a lot of experiment to find out the magnitude at a particular point around the current carrying conducting wire, and based on the result they have got, have given us a law which we call Biot Savart law. So it is Biot Savart law that is going to help us to find out the magnitude of a magnetic field due to a current element. Okay, so let's say they are calling it dB, the magnetic field at point P due to that current element dl. Okay, so dB is directly proportional to current flowing through the current element. dB is directly proportional to the dl, the length of the current element. dB is directly proportional to the sine of the angle the current element has made with respect to the position vector r. Okay, and dB is also proportional to 1 by r square. 1 by r square means inversely proportional. dB is inversely proportional to the square of the distance of the observation point with respect to the current element dl. Okay, so I is basically the current passing through the current element. dl is the length of the current element. Let me write it down for you. Current, please take note everyone, passing through current element. dl is the length. Okay, let me write down the current element as CE. It is going to be a short form. Okay, so the length of the current element, and sine theta is the angle the current element makes, sine of the angle that the current element makes with the position vector r, and r is definitely a position vector of the observation point with respect to the origin at dl. Okay, so this is it. If you're going to combine all of this, what we are going to get, let us see that one. Okay, so after combining all of this, we are going to get dB is proportional to ideal sine theta divided by r square. Okay, so to make that into an equation, we need a proportionality constant, which is mu naught divided by 4 pi, and ideal sine theta divided by r square as before. Okay, so what is mu naught? Mu naught here is called free space permeability. Mu naught is free space permeability. Okay, and mu naught is equals to 4 pi into 10 to the power minus 7 Tesla meters per ampere. Okay, that's it. Now this is the dB is basically the magnetic field due to the current passing through the current element dl at the observation point T. Observation point P. Now what is the unit of magnetic field? Definitely you already have guessed. The unit of magnetic field is Tesla, under the name of Nikola Tesla. Okay, so this is Tesla. Okay, now we are going to move forward and find out the vector form of this Biot Savart law, because we already know that magnetic field is vector quantity and it has a particular direction. From right thumb rule, you clearly find out the direction of the magnetic field at the point P. Anyone? So if this is the direction of the current, we already know, and use our right thumb rule to that. So what is the direction of the yes, this into the screen. But why am I writing cross over there? Anybody have an idea about that? Yes. So here, if you're going to consider an arrow, and the arrow looks like that, you all know this, very common. Suppose an arrow is pointing the direction of the magnetic field, and if an arrow is moving inside the screen, we are going to look only the back of the arrow, right? And the back of the arrow is going to look like a cross or X. Okay, so that is why we call it into the plane of the screen. And if you're going to look from this side, if the arrow is coming towards you, coming out of the paper or the screen, and it is coming towards you, you're going to see the pointy head of the arrow, and that is why it is outward and definitely perpendicular to the plane of the screen. So here I'm writing X to represent the magnetic field is into the plane of the screen. Okay, clear? Now, how the Biot Savart law is going to look like if we write it in the vector form? Let us find it out. So we have dB is equals to mu naught divided by 4 pi ideal sine theta divided by r square. Now we are going to improvise slightly. So we are going to put r and r in the numerator and the denominator. So the equation is going to look like mu naught by 4 pi ideal sine theta, and r is going to be there sine theta, and divided by this one is going to be r cube. Now look closely at this dl into r sine theta. Rings any bell? AB sine theta. What happens to this? How does it look like? Yes, it is going to be A cross B. Very good. Now, if by the same similarity we have over here dl in r in sine theta, it could be dl cross r or r cross del. Which one is the correct one? Anyone? This is a vector and definitely it is have a direction. So dl cross r is a particular direction and r cross dl is going to have completely opposite direction. What is going to be? Which one is the correct one? Number one or number two? Tell me quickly. Okay, you think number one is the correct one? Okay, let's find out why is that. So this is the direction of the current and this is our observation point. Or we can say that dl is in the same direction because we already mentioned that the direction of dl and direction of current is in the same direction. Okay, so dl and this is the r, this is theta, right? So what is the magnetic field's direction in the at P? It is into the screen, right? So if this is dl and this is r, so dl cross r means from dl towards r. If you're going to rotate a right-handed screw, the screw is going to move into the screen. Absolutely. So into the screen, right? So that is the direction of the magnetic field at point P. Definitely, so it is going to be dl cross r because it is pointing the correct direction of the magnetic field, not the r cross dl. Okay, so we are not going to take r cross dl, we are going to take dl cross r. So let us use that. So mu naught by 4 pi I into dl cross r divided by r cube. Okay, so this is the vector form of the magnetic field produced by the current element at the observation point P. Okay, now we are clear about this, right? And if we are going to tell you how to find out the magnetic field for a very long or infinite long straight conducting wire using this Biot Savart law. How to do that? So let us use the Biot Savart law and find it out. Okay, so let us take a very long straight conducting wire like that, and let us have an observation point. Let's say over here, point P, and let us draw a perpendicular from the point P like that, and let us call that particular point as N. Okay. Now we are going to have a current element. This total wire, let us call it XY, and the current is going to flow like that in this direction from X to Y. Okay. Now let us have a current element. So let us have current element DL over here. Okay, this is the current element, let's say DL, and this is the point O. Okay, and what is the position vector of point P with respect to DL? This is it. This is called R vector or the position vector of point P. Now, in this case, we're going to take it as S because this one we're going to take it as R as well. Okay, so this angle is called alpha. This is 90 degree, you can clearly see. And this is theta. This angle is theta as before. Okay, now NO, let us say that NO is L. Okay, this is O, basically this level is O, and NO is L, and NP is R. And now we are going to connect X and P and Y and P as well. Okay, so let us connect X and P and Y and P. So X and P connecting and connecting Y and P. Okay, so this two angles are very special. So let's take this one as phi 1 and the other one as phi 2. Okay. So what we're trying to do actually, we are trying to find out the magnetic field for the whole conducting wire, and to do that, we are going to vary the alpha from phi 1 to phi 2. We're going to get it. Why is it necessary? Okay. So let us write down the Biot Savart law for this current element dl over here. Okay. So dB is going to be mu naught by 4 pi I dl sine theta divided by what square? R square or S square or L square? Which one? The position vector of P with respect to dl is S. So it is going to be S square here. Very good. So what we are trying to do, we are going to find dB in terms of alpha. Okay. So that is why we are going to start with substituting sine theta first. Okay. So here in this triangle, let me point it out. In this triangle, you can see there are three angles, theta, alpha, and 90 degree. So definitely the sum of all this is going to be 180. So theta plus alpha plus 90 degree is equals to 180. So definitely theta plus alpha is equals to 90 degree, and theta is equals to 90 minus alpha. So sine theta is going to be sine 90 minus alpha. That means it's a cos alpha. So sine theta is cos alpha. Now what about cos alpha? So cos alpha from this triangle, again the same triangle, alpha is this angle. Okay. So cos alpha means base by hypotenuse. Base is R, hypotenuse is S. So simply it's R by S. So from this, we can try to substitute S. So S is going to be R by cos alpha, which is basically R sec alpha. Clear everyone? Any doubts until this point? Okay. Don't hesitate to ask your doubts if you have any. Okay. So now S is equals to R sec alpha. And we have sine theta is equals to cos alpha. And now we are going to look for DL, how to substitute DL. Okay. So we have L by R as tan alpha, perpendicular divided by base. So L is equals to R tan alpha, and DL is going to be R sec square alpha D alpha. Okay. So we have all the things we need. Now it's time to put the values. So dB is equals to mu naught by 4 pi I into dl is R sec square alpha d alpha multiplied by, we have S as R sec alpha. So let us put it in the bottom. So R square sec square alpha, and we have sine theta as cos alpha. So we are going to substitute like that, this one. So sine theta as cos alpha. Okay. So let us cancel the terms. We can cancel actually. So R and R square cancels, R remains. Sec square alpha and sec square alpha cancels. Okay, the d alpha remains though. Let me point the d alpha for you. This is the d alpha and cos alpha. Both of them are going to remain. Okay, so we have dB as mu naught I divided by 4 pi, and R is also there, and we have cos alpha d alpha. Okay, now we are going to integrate the dB to find out the magnetic field for the whole wire, and we are going to vary the alpha from minus phi 1 to phi 2. Why it is minus phi 1? Because we are taking negative anything below NP. Okay, so below NP we can see this is the alpha 1, phi 1. So phi 1 is going to be negative, and above NP we are going to take positive. So this one we can take as positive and this one as negative. So minus phi 1 to phi 2. Let us integrate this one and find out the result. Okay. So definitely it is going to be B. So mu naught I divided by 4 pi R, and it's going to be sine alpha, and phi 2 phi minus phi 1. So it is going to be, acha, let me write it down over here. So mu naught I divided by 4 pi R, and it is going to be sine phi 2 minus sine of minus phi 1. Now tell me what is going to happen. Minus of sine of minus phi 1. Yes, the minus is going to come out and it's going to get multiplied with the minus over here, and it's going to be plus. So let me write it down to the next page. So magnetic field due to the straight long conducting wire is mu naught I divided by 4 pi r sine of phi 1 plus phi 2. Both of them are going to plus like that. Okay. Now imagine it is a conducting wire infinitely long, very, very long, infinitely long wire. So in that kind of situation, so let me write it down. For infinitely long wire, phi 1 and phi 2 is going to become 90 degree. So in that situation, B is going to be mu naught I divided by 4 pi r into 1 plus 1, that is 2. So it's going to become mu naught I divided by 2 pi r. Okay, so this is a very, very important formula. Remember, okay, the magnetic field for a infinitely long wire at a observation point. Okay, understood everyone? So what we have learned today, we have learned about Biot Savart law, mu naught I dl sine theta divided by 4 pi r square, and also learned about the direction. Into the plane of the screen is cross, out of the plane of the screen is dot, and we also learned how to find out the magnetic field for an infinitely long conducting wire. Okay, so that's all we have for today. I hope you're clear with this. Any doubt or anyone? Okay, clear. Okay, so let's meet in a next day. Till then, take care everyone. Bye bye.